All right, if you need the first day of Lewis structures practice or notes, if you were absent on Tuesday the 16th, this is for you. Or if you just need a recap of what we did in class that day. Lewis structures, remember, that's when we draw out what the molecules look like and how the atoms are sharing electrons between each other. If you don't have these steps written down in your notebook, make sure you have at least these 4 steps for drawing Lewis structures. And there is actually a 5th step that we will get to in a moment. But I'm going to start working through these steps to draw the Lewis structure for CH3Cl. All right, so the first step is to count up the valence electrons that are in this molecule. So we need to look at our periodic table to figure out how many valence electrons each atom has, and then we can add those up to get the total valence electrons for our molecule. Make sure you have these valence electrons labeled on your periodic table so that you can use it as a reference. So carbon has 4 valence electrons. To that, I'm going to add 1 for each hydrogen, so that's 1 times 3, and chlorine has 7, so that's 4 plus 3 plus 7, that's going to be 14 total valence electrons in this molecule. Next, we need to put the least electronegative atom in the middle and put the rest around that central atom. So I'm going to find the least electronegative element here by figuring out which one is the farthest away from fluorine, since I know that fluorine is the most electronegative. So we have hydrogen, carbon, and chlorine present in this molecule. Hydrogen is the least electronegative, but that's where the exception to the rule comes in, actually. Hydrogen, make sure you have this, hydrogen is never in the middle. So since hydrogen, which is actually our least electronegative, can't go in the middle, that leaves carbon as the next candidate. So carbon's going to go in the middle of my structure here, so I can put my carbon like that. And the rest of my atoms will just go around my carbon. So I'll do 3 H's and a Cl here on the bottom. It doesn't have to be like this, like if you want to put your Cl on the top and your H's around the other sides, it doesn't matter. But there we go. There's step 2. Step 3 is to do my bonding pairs, because these are atoms, right now they're just atoms floating in space. They're not bonded to each other, so it's not a molecule yet. But if I take these electrons and I put them in between my atoms, now I have atoms that are bonded together because they're sharing electron pairs, and now I have a molecule there. Great, so that is step 3. So now, step 4 is where we need to think about the octet rule. What is the octet rule? The octet rule is this idea that every atom wants 8 valence electrons. Except actually there's an exception here. It's hydrogen again. Hydrogen only wants 2. So every atom wants 8, hydrogen only wants 2. Let's come over here and check if we have satisfied the octet rule. Let's look at my hydrogen here. He has 2 electrons right now, which is all he wants, so he's chilling. This hydrogen is also chilling, and so is this guy. How about our carbon? Our carbon, how many electrons does this have? It has 2, 4, 6, 8. So our carbon, our octet rule is satisfied there. But on our chlorine, we're going to notice, no, it is not satisfied, because this chlorine only has 2 electrons, and of course he wants 8. So what I'm going to do is I'm going to satisfy the octet rule on my outside atoms. And I'm going to prioritize my outside atoms. I'm not going to worry about my carbon right now. But my chlorine, like I just said, he has 2 currently, and he wants 8. And that works out because, remember, we have 14 total valence electrons to play with. That means that eventually 14 dots will be drawn here, and then I'll know that I'm done. So I have 6 more that I can give to chlorine, which is perfect because that's exactly what he wants. And now my chlorine has his octet. My hydrogens each have their 2 that they want, and it just so happens that my carbon also has the octet that it wants. So now, since all of my atoms have the octet rule satisfied, and I have used the correct number of electrons. I've drawn the right number of dots. This one is finished. That is the Lewis structure for CH3Cl. Sometimes, though, it's not that simple. So let's try another example here. Let's try SO2. We're going to see that sometimes we have to do some other maneuvering to get the Lewis structure complete. So first step, again, is to count the valence electrons. Sulfur has 6. Oxygen has 6 as well, but I got 2 oxygens, so that's 6 times 2. 6 times 2 is 12, plus 6 is 18 total valence electrons in sulfur dioxide here. Next, I'm going to take the least electronegative atom, and I'm going to put it in the middle of my structure. It's going to be S in the middle and O on either side, or top and bottom, I guess, but either side is easier to draw. Next, step 3, I'm going to do my bonding pairs to make sure these atoms into a molecule, so they're actually bonded to each other. Next, we need to satisfy the octet rule on the outside atoms. So I've spent 4 of my electrons, 1, 2, 3, 4. I have 18 that I have to draw, which means I have 14 left to play with. I'm going to focus on my outside atoms first, because that's what my step 4 says to do. So I gave 6 to oxygen here. Now he's good, because he's got his 8, and I'm going to give 6 to this oxygen over here. Now let's take count of how many we've spent so far. 2, 4, 6, 8, 10, 12, 14, 16. Remember, I have 18 to play with, so I have 2 more that I need to put somewhere. And let's put them on this sulfur, right? Because now that my outside atoms have their octets complete, now I can pay attention to my inside atom, and I can give sulfur the remaining 2 electrons. But there is a problem here. Oxygen does have his octet, and so does this oxygen here, but sulfur is missing 2 electrons. He's only got 6, and of course he wants 8, because he's an atom, and all atoms want 8. So what we're going to do is we're actually going to say to our friend oxygen over here, we're going to say, hey, oxygen, can you please share with sulfur? And now look at what's happened. We've taken our oxygen, which had an octet, and he still has his octet, right? We got 2, 4, 6, 8 electrons around the oxygen. He has access to those 4 in the middle. And our sulfur now also has these 8 electrons. So now our oxygen has his octet satisfied, our sulfur has his octet satisfied, and this oxygen, of course, has his octet, as he did before. So look at what's happening here. Now we have an oxygen which is sharing 2 sets of electrons with the sulfur, and the sulfur sharing 1 set of electrons with the other oxygen on the other side. When we have multiple pairs of electrons being shared, another way to draw that is with these 2 lines, and that represents a double bond. And there we go. So we have sulfur dioxide. Let's try one more, and I want you to try this one yourself. We're going to try CO2. Actually, we're going to do 2 more if we have time. Pause the video here. All right, so this is 6 times 2 again, but this time plus 4, because the carbon's only got 4. This is going to be 16 total valence electrons, and I'm going to kind of jump ahead here. This is where you're at the end of step 4, and you're going to notice that we've spent all 16 of our electrons already, but we don't have any more to give to carbon. We're going to pull the same trick that we did with the sulfur dioxide, and we're going to ask this oxygen to share another pair with the carbon in the middle. And now our carbon has 6 valence electrons, which is better than 4, but still not perfect. So we can get the other 2 by asking our other oxygen, hey, can you also share an extra pair of electrons? And that's how carbon gets its 8 valence electrons, its full octet, is it double bonds with both carbons, it double bonds with both oxygens on either side of it. So we can draw our final answer like this. Now, one more that I do want to try is carbon monoxide. So we just did carbon dioxide. Carbon monoxide is a little bit different. Our carbon has 4, plus 6 from our oxygen equals 10 total valence electrons. And I can put my C and my O right there. put my bonding pair in the middle, and then I'm going to try to fill octets until I run out of electrons. So I can give a full octet to my carbon there, and just one pair to my oxygen before I run out of electrons. I've spent all 10 already. So what I can do here is I can pull the same trick that I pulled earlier, and I can tell my carbon, hey, you got to share with the oxygen. Now that's better. The oxygen has 6 while the carbon holds on to its octet. But that's not enough sometimes. And we can't pull from another carbon because there's only one of them. So we have to ask the carbon, hey, can you share another pair of electrons actually? So now we're sharing a total of 3 electron pairs between the carbon and the oxygen. So this becomes a C triple bonded to an O. That is the structure of carbon monoxide. It's a triple bond. So we can do triple bonds. Now the thing about these double bonds and these triple bonds, you only want to do them when they're absolutely necessary. Let's come back to our steps and add in step 5. We can say step 5 is satisfy the octet rule on, satisfy the octet rule on the middle atom, if you have electrons to do that. And then sometimes, you don't have to do this every time, but sometimes redistribute electrons to make double bonds. But you only do this if you run out of electrons. Remember that the total number of dots that you draw should match the total number of valence electrons that you calculate in step 1, right? So here you have to draw 10 valence electrons. You can't draw less, you can't draw more, because we don't have those electrons to play with, and they have to go somewhere, right? So that is how that works. Now, there's going to be a part 2 to this video with a little bit more examples and going a little bit more in depth, but that's it for now. It's a good intro.